Good morning, all of you. Till now, what we have seen? We have read about biopharmaceutics topic, right? So, you have two kinds of topics in your syllabus. So, what is that, ma? First one is biopharmaceutics. So, and second one is pharmacokinetics. Pharmacokinetics. So, in your syllabus book, they mentioned number 1 biopharmaceutics and number 2 pharmacokinetics. So, your first mid-exam syllabus is from biopharmaceutics. It is of A, D, M and E. Yes, so you have to read all these 4 topics for your first mid. So I completed first mid syllabus. So today I am going to start about pharmacokinetics. So in second you have number 2. Again number 2, introduction to pharmacokinetics, PK. I am writing here short form as PK. So what you learned in this biopharmaceutics topic? You just learned about the mechanisms of A, D, M and E. How the process of mechanism of drug will going to expose its absorption, distribution, metabolism and excretion. In these processes, how the kinetics of the drug will be. How the kinetics of your drug will be. So, if it is going to be absorbed or if it is going to be distributed or if it is going to be converting into other chemical form, that is nothing but metabolism. So, how the kinetics of the drug will be, how it will be produced as its Cmax, T half, AUC and all, etc. So, you have to read so many pharmacokinetics. So, by reading all these kinetic parameters, what you learn? So, you have to know the behavior, kinetic behavior of the drug. So, how it will be behave in your body. So, let me discuss it one by one. So, first one is pharmacokinetics. Under that, I am going to discuss you about introduction to pharmacokinetics. So you have to listen carefully. This topic is very, very important one, ma. Just listen carefully. So what you learn upon reading this kinetic topic, see, the duration of drug therapy will be ranges from a single dose. See, the duration of your drug therapy will be ranges from single dose. Either it may be a 10 or 20 or 30 mg. So when you take the drug of this quantities 10 or 20 or 30 mgs for a single dose to treat acute conditions to drugs, it will be taken as a long life. So if suppose your drugs, your diseases will be of acute and chronic, right? You already know this. Basically, you are a PharmD student, so you already know this acute stage and chronic stage. So, which one will have some severity? Chronic stage. So, in that situation, you need to take a drug for prolonged period of time. That means a long time. So, because this is a situation, you will get a severity. So you have to reduce that severity. You want to take the drug for prolonged period of time. That is nothing but here lifelong. Some drugs you may take for lifelong, right? So you have to take such kind of drugs from a single dose. So single dose. See here, the frequency of administration of a drug in a particular dose. See, the frequency of administration of drug in a particular dose. Suppose you are very well know that PCM, right? Paracetamol. Generally 500 mg is there or 1000 mg is there, right? So it is a particular dose. It is a particular dose. So you have to administer such kind of dose in a frequency manner. Frequency means what? It's a duration. It's a duration. Suppose first 500 mg, you just take it for first hour. That means either 6 o'clock or 7 o'clock. Next tablet, you have to take it, you just give a gap of 12 hours or 6 hours based upon the condition of a patient, right? So based upon the severity condition of a patient. So that is nothing but the duration. How much time you will take, as a duration, either it may be of 6 hours or 4 hours, whatever it is. So the frequency of administration of a drug in a particular dose is called a dosage regimen. So next, coming to this point, the kinetics of drug absorption, distribution, metabolism and excretion. See, the kinetics of drug absorption, distribution, metabolism and excretion, that is nothing but KADME, and their relationship with the pharmacological, therapeutic or toxicological response in man and animals. It is nothing but your pharmacokinetics. See how important it will be. So once you will get an idea to learn this pharmacokinetic, so you can able to justify the drug therapeutic effect, pharmacological effect or toxicological response. So next, other important definitions you have to learn in this pharmacokinetics topic is clinical pharmacokinetics. Clinical pharmacokinetics. It is application of pharmacokinetic principles in the safe and effective management of individual patient. See here, individual patient. And what do you mean by population? Population is nothing but more than one, right? So it is the study of pharmacokinetic differences of groups, differences of drugs. Suppose you have to test one drug, that is Etodolac. Suppose, for example, I am saying you, so it is an anti-inflammatory drug, NSAID. So you want to test the pharmacological effect or therapeutic effect of this drug. You can make the people into two groups. This group is consisting of 100 people and this group is consisting of 200 people. So you can test the therapeutic efficacy of the products in two different groups. So that is nothing but it is the study of pharmacokinetic differences of drugs in various population groups. This 100 and 200 is nothing but population groups. So you have to test the efficacy of the product in these population groups, right? So this is nothing but population pharmacokinetics. It is very, very interesting topic, ma. This is toxicokinetics. You know that, toxicokinetics. It is the application of pharmacokinetic principles to the design, conduct and interpretation of drug safety. See, ma, how much the drug will be safe. Either your drug may be safe or unsafe, or it may be produces some toxicity or not. So you can able to know by knowing the pharmacokinetic principles of each drug. So you can test the efficacy, pharmacological activity, therapeutic efficacy, okay, and then you have to know the drug safety. That is nothing but either it may be produces some toxic reactions or not. All the principles will be dependent upon the pharmacokinetic properties of a drug. So then, before going to learn in detail about pharmacokinetic principles, you have to learn the plasma drug concentration time profile. So what is the importance? Why we have to learn this? So by learning this plasma drug concentration time profile, you may get pharmacokinetic parameters and pharmacodynamic parameters. See, ma, a direct relationship, it will be a direct relationship which will be exist between the plasma drug concentration at the site of action and the concentration of the drug in plasma. So you have to evaluate pharmacokinetic parameters and pharmacodynamic parameters by knowing the relationship of a drug between the plasma drug concentration and time profile. See, ma'am. So suppose you want to evaluate pharmacodynamic properties or pharmacokinetic properties. So you have to know the relationship of a drug between plasma drug concentration and time profile. See how it will be. It's a graph. You have to learn this graph as it is. It's a graph. It is showing that plasma drug concentration versus time profile after oral administration of single dose of a drug. See, when you take a single dose of a drug for oral intake, so how it will be useful to evaluate you for the pharmacokinetic properties and the dynamic properties. Let me discuss it one by one. See, ma'am, how you have to learn this graph. See, everybody, you have to focus on the screen. When you plot a graph between, this is an x-axis and this is a y-axis, no, right? Then it will showing some graph like this. So when you plot a graph between time versus plasma drug concentration, that means your drug will be available in plasma. So when you take the time and x-axis and plasma drug concentration on y-axis, it will give a relationship when you will take the drug by oral delivery with a single dose, right? So here this is called onset of action. Onset of action. And this is called at here where you will get some peak, that means height. See here, this is a height, right? So this is called Cmax. So where you will get a peak like this is called Cmax. And the area which will be available under this peak is called AUC. The area which will be available under this peak, it is called AUC. And this is the left side and this is the right side of the curve, right? So this left side of the curve is representing you the absorption of the drug. See, ma, left side of the curve is representing you the absorption of the curve. And the right side of the curve representing you the elimination. See here, when the drug will be starting to produce its action. What do you mean by onset of action? The drug is in the beginning state. It is ready to produce its pharmacological action. So that is nothing but the beginning of the pharmacological effect is nothing but your onset of action. Here your drug will be ready to produce its effect, therapeutic effect, right? This is nothing but onset of action. This onset of action is nothing but one of the pharmacodynamic property of a drug. Okay, so then what are the pharmacokinetic properties of a drug? See here, ma, I am writing PK is nothing but pharmacokinetics. You just remember this word PK, pharmacokinetic. So here you have three different kinds of pharmacokinetics. First one is Cmax, and next one is Tmax, and third one is AUC. Okay, so these three are pharmacokinetic properties of a drug. First, you just focus it on Cmax, Tmax, and AUC. So, what these three parameters will exactly telling you? CMA. What do you mean by Cmax? Cmax is the maximum plasma drug concentration which will be available to produce its therapeutic effect. So, here the plasma drug concentration will be maximum. So, this is nothing but this is also called as peak height concentration. This is also called as peak height. So, here it is representing some height, na? So, that's why peak high concentration. That is nothing but Cmax. It is representing the maximum plasma drug concentration which will be useful to produce its therapeutic effect. So this is nothing but Cmax. So in this Cmax, you have a right side curve and left side curve. Sorry, see here right side curve and here left side curve. Left side curve of the Cmax will represent you the absorption phase of the drug. And right side curve of the Cmax will represent you the elimination phase of the drug. Here the drug will going to eliminated out. And at the Cmax, how the relationship of absorption and elimination? Both are equal. At the Cmax, your absorption is equals to elimination. See carefully. So at the Cmax, your absorption as well as elimination will be equal. In this absorption phase, your elimination will be less. In this elimination phase, your absorption will be less. See, very simple. You just concentrate what I am telling. So this is about the Cmax. So what are the parameters? What are the parameters will be dependent upon the Cmax? See, what are the parameters? Parameters will be depends upon the Cmax. What is that? 3 parameters will be dependent upon Cmax. First one is onset of action. Onset of action and rate of elimination. Sorry, first rate of absorption and then rate of elimination. Rate of elimination. See here, by knowing the drug Cmax, by knowing the drug exact Cmax, you can able to find out the onset of action of the drug, the rate of elimination of the drug, and rate of absorption of the drug. See how important the Cmax is. And then you have Tmax. The second pharmacokinetic parameter is nothing but Tmax, right? So what do you mean by Tmax? What do you mean by Tmax? T stands for time. The time to reach Cmax is nothing but a Tmax. The time to reach the Cmax is nothing but a Tmax. So this Tmax is also useful for estimating the onset of action and the duration of action. So Tmax is useful to calculate the onset of action and duration of action. Both actions can be calculated using Tmax because it is showing you the time difference, right? So onset means the beginning of the time and the duration means the time period. Period is nothing but the duration. So you can calculate very easily these two pharmacodynamic parameters using Tmax values. So then the third pharmacokinetic parameter is AUC. So the name itself is indicating area under the curve. This is a curve, this is a peak curve, this is the area which will be available. The plasma drug concentration will be available under this area. Under this area, the plasma drug concentration will be available under this area will be useful to calculate the amount of the drug. To calculate the amount of the drug. Amount of the drug which will be available to produce its therapeutic effect. So this is a peak. The area available under the peak will be useful to calculate the amount of the drug which will be produce its therapeutic effect. So these 3 parameters are the pharmacokinetic parameters: Cmax, Tmax, AUC. And next, what about pharmacodynamic parameters? See here. Seema, what I told you, 2 categories can be evaluated from the plasma concentration profile: pharmacokinetics and pharmacodynamics. Pharmacokinetic parameters are Cmax, Tmax, and AUC. See, it is very, very important, these three parameters. In your exam point of view also, this plasma drug concentration versus time profile relationship is the most important question. That's why I'm stressing you in this topic. And this AUC is also useful to calculate the bioavailability of the drug. Why? It will be available under under the curve, right? So how much amount of the drug will be available to produce its therapeutic effect is nothing but your bioavailability. So here your AUC is useful to calculate the bioavailability of the drug also. And what are the pharmacodynamic parameters, right? So here you are going to learn about the pharmacodynamic parameters. See here, I am going to draw one more. If you see all these dynamics and kinetics in one graph, it may get some confusion. That's what I am drawing and I am explaining for you people. You just listen carefully. So same when you take the relationship between plasma drug concentration versus time. See here, this is the minimum effective concentration, MEC, minimum effective concentration, MSC, maximum safe concentration, or maximum safe concentration, or also called as toxic level, or MTC. Above this it is a toxic, above MSC it is a toxic. This is called MSC, maximum safe concentration, or maximum of tolerable concentration. See, minimum effective concentration, maximum safe concentration. Your drug peak will be like this. So, above the plasma drug concentration, if your plasma drug concentration will be above the MSC level, it leads to produce some toxic effects, right? So first you have to know about MEC. First pharmacodynamic. Here I am going to write PD parameters. First one is MEC. What do you mean by MEC? It is defined as the minimum concentration of the drug in the plasma. SEMA. It is defined as the minimum concentration of the drug in the plasma is required to produce its therapeutic effect. So what does it mean? It's a minimum concentration of the drug in the plasma to produce its therapeutic effect. This is nothing but MEC. So which kind of drugs will comes under this MEC? Example is antibiotics. So why here I am telling you antibiotics as an example? In case of antibiotics, minimum effective concentration is sufficient to kill or to inhibit the growth of what? Microorganisms. Is it right? So in such cases of antibiotics, your MEC is sufficient to kill or to produce microorganism. That is nothing but here your antibiotics are effectively efficient in MEC level, minimum effective concentration. That is minimum of plasma drug concentration is sufficient to produce its therapeutic effect. Because of antibiotics require MEC to kill or to inhibit the growth of microorganisms. And next pharmacodynamic property is maximum safe concentration. It is the concentration of drug above the MSC. It leads to produce some unwanted effects or toxic effects. See here. Maximum safe concentration is a concentration of the drug in the plasma. Above this MSC, the drug will leads to produce toxic effects or also called as unwanted effects. And then the third pharmacodynamic property is onset of action. Onset of action. That is nothing but the beginning of pharmacological response. Here it will be. It's a beginning. So it is going to start its pharmacological effect. This is nothing but onset of action. And next, fourth one is the duration of action. The duration of action. It is a time period of a drug for producing its therapeutic effect. It's a time period. And next, fifth one is intensity of action. Intensity of action. What do you mean by intensity? Intensity is nothing but the maximum of therapeutic effect. Maximum of therapeutic effect. So the intensity of action is maximum of therapeutic effect or maximum of pharmacological effect it will be produced by your drug. And then the sixth one is therapeutic range. Therapeutic, TH stands for therapeutic range. So what do you mean by therapeutic range? See here carefully. If your drug will be producing its action, what is that action? Therapeutic action of a drug will be produced between this MEC and MSC. See ma'am, suppose here it is 100 micrograms of plasma drug concentration. Here it will be 10 micrograms of plasma drug concentration. If your drug will be producing 50 micrograms, it is able to produce its therapeutic effect, right? So in that case, your drug will existing its therapeutic effect within the range. Within what range? Within MEC and within MSC, right? So this is nothing but therapeutic window. So the drugs which will able to produce their therapeutic effect within this therapeutic window range. That means between this MEC and MSC level, then those are said to be therapeutic range drugs. So these are of different kinds of pharmacodynamic properties which will be estimated or which will be analyzed using plasma drug concentration versus time profile curve. In your exam point of view, directly they will ask you to write the relationship between the plasma drug concentration versus time profile. So you need to explain the definitions as it is by explaining with your graph. You have to learn this graph. See ma here once again. See, this is the graph what I drawn for you. See, this is the beginning of pharmacological action, onset of action. This is the time period, that is nothing but duration of action. This is the termination of action, that is ending of the pharmacological action. And this is the elimination phase. See, this is the absorption phase. See, Cmax, absorption rate is equal to elimination rate. So Cmax is called peak plasma concentration. Above this MSC, above this maximum safe concentration, you have a toxic level. And this is the minimum effective concentration, that is MEC. See, this is nothing but your area under the curve. See ma, what I have drawn for you, the graph is exactly right. So you have to learn this graph, okay, to explain your pharmacokinetic and pharmacodynamic parameters. So this is about your pharmacokinetics introduction, how it will be useful to calculate the drug therapeutic efficacy. The drug therapeutic efficacy which will be based upon pharmacokinetic and pharmacodynamic properties. So by knowing the dynamism of, by knowing the kinetics, you can able to find out the dynamic properties of the drug also. And the next topic which will be in your syllabus, that is nothing but rate constant and orders of reactions. So here you are going to learn about first order and second zero order reactions. See, rate means the velocity with which a reaction or a process will be occurred as its rate. Order of reaction, it's a manner in which the concentration of the drug which will be influences the rate of reaction. So here in these reactions, your drug concentration will be affecting your rate of reaction process. See how it will be. Consider the following chemical reaction. Your drug A is forming your drug B. This is considered as a order of reaction. So how you can express the rate among this equation? How you can express it? Minus dA by dt. Suppose the rate for drug capital A. The rate for this drug capital A product, you can express the rate by minus D capital A by small d small t. The negative sign indicates the concentration of drug A will be decreases with the time. See here, this negative sign will indicate the concentration of drug product A, which will be decreases with the time t. So that's why minus dA by dt. As the reaction proceeds, the concentration of B increases the rate of reaction. So that means you can express it dB by dt. That's it. Here no negative sign, nothing. Why? Because your concentration of drug product B is increases with the time. So that's why here no negative sign. Then you have to remember this entire equation to learn first order and zero order. What is that entire equation? dC by dt. This C is capital C. Here capital letters and small letters are very, very important. That is equals to minus K C to the power of N. See, my dC by dt. dC by dt is rate of reaction is equals to minus K is constant, C is the concentration of the drug, and N is, if it is N is 0, it will follow zero order kinetics. If it is 1, it will follow first order kinetics. What? N. See here, C to the power of N. If it is 0, it will follow zero order. If it is 1, it will follow first order. If it is 2, it is following second order reaction. So that is nothing but N. So you all should remember this equation for entire pharmacokinetics topic. dC by dt is equals to minus K capital C to the power of N. That's why I am telling you, you have to write it on the paper. Don't listen the class blankly. Just write it. Order of a reaction. The manner in which the concentration of drug will influences the rate of reaction or process is called a order of reaction. So you already know this general equation. dC by dt minus K C to the power of N. C to the power, not here, just write here N. K is rate constant, N is order of reaction. Either it may be 0 or first or second. That is nothing but order of reaction. And then basically 3 types of kinetics are encountered. Basically, here you don't have second order kinetics in your syllabus. That's why basically 3 types of kinetics are encountered. Zero order, first order, mixed order. Zero order, first order, mixed order. Then first I would like to discuss about zero order kinetics. So what is your equation? dC by dt is equals to minus K C to the power of N. This is the basic equation, right? So if N is equals to 0, if N is equals to 0, your equation will become minus K 0 C 0. Why? Because here this 0 is indicating you that it follows zero order kinetics. So the constant is also 0. K is 0 into C to the power of 0, where K0 is zero order rate constant. See ma'am, K0 is zero order rate constant. So how you will be defined this zero order process? It can be defined as the one whose rate is independent. See, whose rate is independent of the concentration. What I told you previously, when one student has raised one doubt. See ma clearly. Your zero order process can be defined as the one whose rate is independent of the concentration of drug which will be undergoing the reaction. That is, the rate of reaction cannot be increased further by increasing the concentration. If you increase the rate of reaction, if you decrease the rate of Okay, your concentration of the drug will be independent. The drug concentration will be independent. This word is very, very important. Without writing this word, you can write all this this is definition. It is waste of time. You will not get any marks. Okay, so the concentration independent reaction is zero order process. Finally, it will be C is equals to C naught minus K naught into T. Okay, this is the equation, final equation of zero order process. Here, if you observe this graph, here you have two different graphs. See ma, when you plot the graph between the time versus rate of reaction, see, dc by dt, you will get a steady state drug loss. You will get the curve like this. It will be indicating steady state drug loss. So the drug will be lost in a steady state manner. So when you plot the graph between time versus plasma drug concentration, you will get a straight line like this. So here, this attached line, see ma, in this where I am rounding it here it is C naught. C naught is nothing but initial plasma drug concentration. That is nothing but C0, initial plasma drug concentration. Slope is minus K naught. Why? It will be a zero order. That's why your slope is representing minus K naught. So when you plot the graph between rate of reaction and between the concentration versus the time, the graphs are showing like this. This is about the zero order kinetics. So it's a constant rate process. The zero order kinetics are also called as it's a constant rate process because we will get the curve like this, right now. So what we have seen previously. So here K naught is zero order rate constant. After rearrangement and integration, this equation will comes out to be C is equals to C naught minus K naught into T. With respect to the time, your concentration will be varied. So here you will get time. So this is the final equation for zero order kinetics. So just write it. C is equals to C naught minus K naught into T. With respect to the time, your plasma drug concentration will be varied. And then you have a zero order half-life. Half-life will be representing you with T half. See, this is a small t and you have to write half like this. T half is equals to C naught divided by 2K naught. See, C naught means you have to write down like suffix C. C naught divided by K 2K naught. This is your half-life, zero order half-life. The half-life of zero order is proportional to the initial concentration. Is it right? So if it will be like this, it will be like proportional, right? So it will be inversely proportional. See, it is proportional to the concentration. Which concentration it is? Initial concentration of the drug. So the half-life of zero order is proportional to the initial concentration of the drug, that is C0. And it will be inversely proportional to the K naught. T half is equals to 1 by 2 K naught, right? Instead of C naught, I am writing here 1 for easy understanding. Okay. So that is what 1 by K naught is nothing but it is inversely proportional, right? So it is inversely proportional to the constant value. Okay, half-life will be inversely proportional to the zero order constant value. So examples for this zero order is controlled drug delivery systems such as implants or osmotic pumps will follows independent of drug concentration. That means these will follows constant rate processes, nothing but zero order kinetics. What are the examples? Implants or osmotic pumps. And the administration of drug as a constant rate, that is IV infusion. How the drug will be passes through the IV infusion? It will be a constant process. It will be released the drug in a constant manner. So these kinds of drug will be follows this zero order kinetics. So this is about zero order rate process. Tomorrow I will discuss you about the first order process. Okay. So here you have to remember the basic equation, then these two graph, then the half-life up to this part. So the zero order kinetics are independent of plasma drug concentration. So the drugs which will undergo IV infusion, implants and osmotic pumps will follow this kind of reaction process. Okay. So this is about the introduction of this pharmaco